This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 1. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 1 involves the graph of g prime, the derivative of a twice differentiable function g. The graph of g prime has exactly one horizontal tangent line in the interval -1 to 10 at x equals 4.2. The plane region R is in the first quadrant, and it's bounded above by the graph of y equals g prime of x, below by the x-axis, and on the left by the y-axis. And we also know that g of 0 is equal to -7, g of 9 is equal to 12, and the definite integral of g of x from 0 to 9 is 27.6. In Part F, the student needs to evaluate a definite integral, and we expect the student to show the computations that lead to their answer. Here are the key concepts needed to solve this problem. There are two basic properties of the definite integral that are needed here. The first is that constants pass freely through integral signs. And the second is that the integral of a difference is the difference of the integrals. Now, as an aside, it seems to me like these basic properties of definite integrals have been tested more regularly on the AP Calculus exam. The other important idea that we'll need to solve this problem is what I might call the backward power rule, but it's often just referred to as a basic anti-differentiation rule. It says if f of x is equal to x to the n, where n is not equal to -1, then n antiderivative of f is capital F of x equal to x to the n plus 1 divided by n plus 1. Let's use these ideas to solve this problem. In the first step, I used the concept that the integral of a difference is the difference of the integrals. Here, I brought the constant 1/2 through the integral sign, and I wrote the square root using an exponent. The definite integral of g of x from 0 to 9 is given in the statement of the problem, 27.6. And we can use the basic anti-differentiation rule on the second integral. Next, we evaluate the antiderivative at the upper bound and the lower bound and subtract. And a little simplification gives us a final answer of -4.2. Here are the scoring guidelines for Part F. This problem is worth 3 points. The first point is for demonstrating the use of the appropriate properties of definite integrals to solve this problem. Notice this is plural. The second point is for correctly writing an antiderivative of the square root of x. And the third point is for the final answer, and again, a final numerical answer does not need to be simplified. Here are some interpretations of these guidelines to help understand how points are earned. To earn the first point, the student needs to convey the correct use of both properties of definite integrals. The second point is for use of the anti-differentiation rule. Well, the correct use of the rule, of course. And at the calculus reading, we often talk about the minimal work needed to earn all of the points in a problem. This is kind of like a line in the sand for the problem, and this would earn all 3 points. It's minimal communication, and we certainly encourage more, but we think it demonstrates use of the properties, the anti-differentiation rule, and it is the final answer, unsimplified. In Part G, the student needs to evaluate a limit, and they need to show their computations that lead to the answer. This is another reminder that we really want to see good communication skills. In order to solve this problem, we'll need to use Lhopitals Rule. Now, I won't read through this entire statement. It basically says that if we have a limit in an indeterminate form of type 0 over 0, or infinity over infinity, then we can find the limit of this quotient by taking the limit of the quotient of derivatives. Now, as another aside, this concept has been tested pretty regularly since its reintroduction into the AP Calculus curriculum. And to earn full credit on a problem like this, good communication is extremely important when using this rule. Let's take a closer look at Lhopitals Rule. In words, Lhopitals Rule says the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided, of course, that the given conditions are met. It's very important to verify that the original limit is an indeterminate form of type 0 over 0 or infinity over infinity. You cannot arbitrarily apply this rule to any limit of a quotient. Lhopitals Rule is also valid for one-sided limits and for limits at infinity or negative infinity, again, provided that the conditions are met, that the limit is in one of those indeterminate forms. I know I get too excited about this stuff, but this is a pretty amazing technique. And a proof of a special case of this rule is usually presented in AP Calculus texts. And there's a very nice visualization of this special case using technology. It's available in a calculator application on the TI website. Lhopitals Rule can be used repeatedly. That is, after applying the rule, the limit may still be in an indeterminate form. So we can use Lhopitals Rule again and again, if necessary. And finally, I don't want to mislead you. There are other indeterminate forms associated with limits. These are not tested on the AP Calculus exam, but I think most college calculus courses cover these forms. The basic approach to solve a limit involving one of these forms is to rewrite the expression so that it is in an indeterminate form of type 0 over 0 or infinity over infinity. And then we know what to do. We apply Lhopitals Rule. Looking ahead, we'll also need the product rule to solve this problem. It says that if f and g are differentiable, then the derivative of f times g is f times the derivative of g plus the derivative of f times g. And let's take a quick, closer look at this rule before we solve the problem. In words, this says the derivative of the product of two functions is the first function times the derivative of the second plus the derivative of the first function times the second function. And here's a way we can write the product rule more compactly using prime notation. And as you might expect, the product rule can be extended to the product of three differentiable functions. Do you see the pattern here? I'm sure you can predict the derivative of the product of four functions. To solve this limit, the first thing we'll do is examine the limit of the numerator and the denominator separately. To find the limit of the numerator, I'll use a property of limits. The limit of a product is the product of the limits, provided that the limits exist. Now, each of these functions is continuous, so the limit as x goes to 0 of x is 0, and the limit as x goes to 0 of the cosine of x is the cosine of 0, or 1. So the limit in the numerator is 0. In the denominator, the limit of a sum is the sum of the limits, again, provided that the limits exist. The function g is continuous because it is differentiable. So this limit is g of 0 plus 0 plus 7, which is also 0. So that means that the original limit is indeed in an indeterminate form of type 0 over 0, and that means we can apply Lhopitals Rule. So let's apply Lhopitals Rule. Take the derivative of the numerator and the derivative of the denominator. In the numerator, we need to use the product rule. And in the denominator, the derivative of g is just g prime, the derivative of 2x is 2, and the derivative of 7 is 0. Now I can evaluate the limit. All of these functions are continuous, so I can just plug in 0, and a little simplification leaves 1/3. Here are the typical scoring guidelines for this type of problem. It's usually worth 3 points. The first point is for verifying the conditions necessary to apply Lhopitals Rule, and that means verifying that this limit is indeed in an indeterminate form of type 0/0. The second point is for evidence of applying Lhopitals Rule, that the student has attempted to take the derivative of the numerator and the denominator in the context of the limit problem. And the third point is for the final answer. And again, remember that a final numerical answer does not need to be simplified. Here are some interpretations of these guidelines to help understand how points are earned. The first point is earned for verifying that both the numerator and the denominator approach 0. In general, the student does not need to reference continuity or differentiability to evaluate either of these limits. That would be nice, but it's usually not necessary to earn the point. In the past few years, any notation that includes equal 0/0 does not earn the first point. It doesn't bother me, but it's that equal sign that bothers some people. And this equality can appear in disguise. That means in an unsimplified expression with an equal sign. Other expressions that are acceptable ways to indicate an indeterminate form include an arrow and the fraction 0/0, or the phrase equals indeterminate form 0/0. The second point is earned for presenting a limit of a fraction with numerator and denominator that are clearly attempts at derivatives. There's certainly some professional judgment here in awarding this point. The second point can be earned without proper limit notation, but the response must in some way convey a limit. And again, we generally use some professional judgment. And finally, the third point is earned for the correct final answer, 1/3. In part H, a new function, oddly enough called h, is defined in terms of a definite integral. And we need to find h' of 3, and of course, show the computations that lead to the answer. The key concept needed to solve this problem is the Fundamental Theorem of Calculus, and what is often referred to as Part 1 of the FTC. If f is a continuous function on the closed interval a to b, then the function g defined in this manner, and I often call this an area so far function, is continuous on the closed interval a to b, differentiable on the open interval a to b, and the coolest part of this, g' of x, is equal to f of x. This is an absolutely amazing result, and it provides the connection between differential and integral calculus. And there are lots of nice visualizations using technology to help discover this result. One other thing here. Notice that there are two variables, x as the upper limit and t as the variable of integration. And I believe there should indeed be two different variables here. These placeholders are being used in different ways, and therefore they should be different. Let's take a quick, closer look at this concept. In words, this says that the derivative of a definite integral with respect to its upper limit is the integrand evaluated at the upper limit. And here's some other notation to show the result of the Fundamental Theorem of Calculus. This shows, perhaps a little better, that integration and differentiation can be thought of as inverse operations. What one does, the other undoes. Now, to solve this problem, we'll also need to use the chain rule. And I won't read through this entire statement with you. This gives us a method for finding the derivative of a composite function, capital F of x, is f of g of x. To find capital F prime of x, we start at the outside taking derivatives and work our way inside. So capital F prime of x is equal to little f prime of g of x times g prime of x. And here's the chain rule using Leibniz notation. The chain rule is a pretty important concept, so let's take a closer look at this idea. In words, this says the derivative of the composition of two functions is the product of the derivative of the outer function evaluated at the inner function and of the derivative of the inner function. Here is some other common notation to illustrate this rule. We often use an open circle to represent the composition of f and g. And here, just another common way to indicate the derivative. And this is a step-by-step procedure for applying the chain rule. I find that this is helpful for my students when they first learn this rule. The most important part, and perhaps the most difficult thing about applying the chain rule, is to identify the outer and the inner functions, f of x and g of x. And this just takes practice. Then, find f prime of x and g prime of x separately. And finally, put everything together and write the derivative of the composite function as f prime of g of x times g prime of x. And here's a kind of visualization of the chain rule. To find the derivative of a composition function, we take the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Finally, let's put all of these concepts together to solve this problem. And I'm going to start by finding the general derivative h prime of x. H prime of x is the derivative of this function defined by an integral. Now, the way that I see this, there are two issues I have to deal with. The variable is in the lower bound, and that lower bound is actually a function of x. First, I'll use a property of definite integrals, and that is, if I reverse the bounds, or the limits of integration, I need a negative sign in front. Since the upper bound is now a function of x, not just x alone, I'm going to have to use the chain rule. And this is actually a composite function, so I will rewrite the expression letting u equal x squared. Now, if I take the derivative of this expression, it's the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Using the Fundamental Theorem of Calculus, I now have minus g of u times du dx. I'll bring everything back to the x world using the original connection between u and x, and simplify. So here's an expression for h prime of x. And then I'll simply find h prime of 3. We're given that g of 9 is 12, so h prime of 3 is equal to minus 72. Here are the scoring guidelines for part h. This problem is worth 3 points. 1 point for the Fundamental Theorem of Calculus, 1 point for using the chain rule correctly, and 1 point for the final answer. Here are some interpretations of these guidelines to help understand how points are awarded. The first 2 points can be earned in either order, and in fact, most students earn these 2 points simultaneously in one expression. We need to see g of x squared for the student to earn the Fundamental Theorem of Calculus point. And we need to see 2x for the student to earn the chain rule point. Note that if g of 0 appears in the expression for the derivative of h, or in the calculation of h prime of 3, then the FTC point is not earned. Here are some example responses and how each is scored. If we see g of x squared times 2x, this earns the FTC point and the chain rule point. G of x squared earns the FTC point, but not the chain rule point. G of x squared minus g of 0 does not earn either point. And this last expression earns the chain rule point, but not the FTC point. There is an eligibility criteria for the third point. The student must earn the first 2 points, to be eligible for the third, and it must be our answer minus 72. Note that the negative sign is associated with the answer point. So if the student does not account for the bounds reversal, they cannot earn the third point. And finally, there is an alternative version of the FTC that some students present, and that would earn the first 2 points. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts, and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.